to go over those in class. So let me pull up some problems. I'll go over the details as well. Okay, so let's copy this problem down, and then we'll walk through it together. So we want to think of these as regions on the graph, okay? Negative would indicate below the x-axis, positive would indicate above the x-axis. But we gotta be a little bit careful with this. So yeah, just give you guys another minute, make sure you have this down, and we'll go through step by step with even and odd functions. And if we need to do another one, we can. Okay. So we have a given region, we have another given region, and then we're going to be asked to find an unknown region. Okay. So let's start off with assuming that the function is even, or let's say the problem tells us we have an even function. So that means we want to create a situation where our graph is mirror images on both sides of the y-axis. Okay, so we're going to start off here. I'll put this over here. F of x is even. Okay, now this region, something's a little strange about this interval. Can you guys indicate what is strange about this interval here? What's off about this interval? Let me ask you this. What do you notice about the bounds?
Both negative?
Okay, something else, something else. This is okay. This is a little strange. You see the distinction?
Would it be because -2 is larger than -4?
Right, so we're not used to seeing something that, we're basically, this is information that's given to us backwards, right? Our lower bounds is usually a smaller value than upper bounds. But here, that means we have to read backwards. So let's rewrite this in something that is more straightforward, right? Reading something backwards means that everything is backwards from this information. So I'm gonna redo this information here. So I'm gonna say the integral from -4 to -2 is really what? If I flip the bounds, what happens to my value? Opposite sign, right? So 3. So this is more straightforward. So I can sketch the graph now and just see it the way it is, right? It's +3. But saying that if I go backwards is negative, that's kind of strange, right? So let's put it in, let's go from left to right, or from smaller to larger. Okay, so I'm going to rewrite this here. All right, so now it's more straightforward, okay? We have two regions. We're going to sketch both those regions. Now here are a couple of tips as to how you're going to create your graph. First thing, sketch the shorter interval first. Okay, don't look at the value. The value has no bearing. Look at which covers a shorter interval. So which covers a shorter interval? -4 to -2, or from 0 to 4? Yeah, this is a smaller interval, right? So you're going to sketch that smaller interval first. Okay. Next step, once you've sketched that smaller interval, fill the other side using even and odd properties. Don't look at the larger interval first. Do as much as you can with that shorter interval. And then once you've done everything you can with the shorter interval, then you can fill in the gaps with the larger interval information. Okay, so let's go through this step by step. Integral from -4 to 2 is where we're going to start. So let's just create a region from -4 to -2, and let's call it 3. Right, so let's just create a region and call it 3. Okay. Okay, so far? Now it's an even function, so let's not look at this yet. If it's an even function, what else can we put onto our graph? Okay, mirror image. So what also must be true?
2 to 4.
2 to 4.
Wait, why is it here?
What's the question?
Why was it here?
Oh, why is this over here?
Yeah.
Because it's an even function.
Right.
So even function means you're going to get mirror image, the duplicate on both sides of the y-axis. All right, so we've done everything we can with this shorter interval. Are we good here? Okay. Now, let's move on to the larger interval. The larger interval, we're going to fill in spaces. Now, this whole region from 0 to 4, is going to be 7. But we're not going to overlap this region and call it 7. Okay, this is already set in stone. Okay, these two intervals are set in stone. We don't want to be touching it. We don't want to be changing it. But instead, we're going to fill in the gaps with missing information so that we can, because of the sum that we know about that interval. So if I know this full region is 7 and this is 3, that means the missing part must be what? 4. So I'm going to create a larger region here. I'm going to call it 4. So if this region is 4, what else do I know? Also 4. So now we have everything filled in. We can answer our question. Our question is the integral from -2 to 4. Careful. Just because you have all those numbers in front of you doesn't mean that you're going to be adding all of them up. You're only adding the intervals of your bounds. What's that equal to?
11.
11. Okay. Any questions with evens?
Can you plot us this? Did you do it without graphing?
No, we graphed.
Okay.
Yeah, it's easier to see the graph, right? It's hard to visualize it. Okay, part B, let's do a function that is odd. So same information, but now function is odd. Okay. So we'll go from -4 to -2, we'll call it 3. So if this region is 3, the difference with odd is that we're creating equal but opposite on the other side. So if this side is 3, then this side is going to exhibit what? There you go, -3. We've done everything that we can with this property. We've sketched the shorter interval. We filled in the other side with our odd properties. And now we can go to our larger interval. Our larger interval is from 0 to 4, which is 7. So now I want this whole region to total to be 7. If this is -3, then this has to compensate, right? What's What is this region? Yeah, it's going to be much larger now. Ten minus 3 is 7. Okay, that's a true statement. If this is 10, can we fill in another gap?
On the other side, would it be negative 10?
Negative 10, right? So we're going to have odd properties all over the place. If I have a true odd function, I should be able to total all the values. As long as I'm same distance away from the y-axis, it should all be 0. 3 minus 10 plus 10 minus 3 is 0. Negative 10 plus 10 is 0. So once you have that, then we can find the integral from negative 2 to 4. Negative 10 plus 10 minus 3. All right, how do you guys feel? Do we need to do another one, or you think you're okay?
Good.
You good? Okay, on Teams, how do you guys feel?
Good.
Good? Any questions?
No.
Okay. All right, let's do a second theorem here. So let's review what second fundamental theorem is. It looks complicated, but we're gonna do a shortcut. We're gonna find the derivative of a definite integral of a function. And if you're looking at this going, boy, that's a lot of work, finding the integral and the derivative. But the good news is we're gonna skip all this process because we know that they're just going to undo each other. It's like saying, if I add 3 and subtract 3, I haven't gone anywhere, right? So I'm not gonna, so if I know they're gonna cancel out, I'm just going to jump to the answer. I'm not gonna spend the time to add 3 and subtract 3. Basically, that's what's happening here. But there is something to keep track of, is that this process, even though we're doing and undoing a process, even though this function is not changing, this variable does get impacted because of these process. And we just have to keep track of what happens with that variable. So what's going to happen is that this upper bound through this process is going to end up getting lodged into the function. In the derivative, it's going to end up taking that function and producing a p prime. So before I go to, and this second adjusted theorem is saying that if my upper and lower bounds are both variables, then I got to do that process for the upper bound and lower bound. But if my lower bound is just a constant, then it's just going to be a 0 here. So I'm going to subtract the 0 and nothing is going to come out of that. So here's the first example here. Let me write this separate sheet here. So I have my function. My function has the integral notation in it, but I'm going to find the derivative of that function. So basically, I'm going to be finding the derivative of this integral. So this matches nicely with our formula, right? We're going to ignore these two processes for this function, and just focus on what the rule tells us. Okay. So what is f of p of x going to look like with this problem? Okay, so what can we do with square root of x?
Okay, for t.
There you go. Put it in for t. Okay, I'm just following what the rule tells me here. Times p prime. So how do I find the derivative of square root of x? Square root of x is the same thing as what? X to the...
1/2.
Yep, just go through power rule, right? Go through power rule. 1/2 x to the negative 1/2. Okay, clean that up. Bring the x down, convert it to a radical. We see some reducing here. Okay, any questions with this process here? Okay, everybody good? All right, what if we do this problem here? Oh, yeah, let me, here's example 2. All right, what's different about example 2 compared to example 1?
There's an x in the bottom.
There we go. So we basically, it's just going to stretch out the problem a little bit longer. Whatever you did with the upper bound, you do the same thing with the lower bound, but then just insert a minus between. Okay. So I basically copied the same problem here. So my upper bound is going to give me the same result. Okay. Repeat the same process with my lower bound. Replace all my t's with my lower bound. Times my lower bound's derivative. All right, so do all my steps make sense? Do you want me to, do I need to clarify anything before I clean up? Okay, so this is going to clean up to the same place as this. I'm going to skip some steps. I already did all that work here. All right, multiply my numerators together, 2x cubed. There's no need to clean up your expression. You can leave it unsimplified, or no need to find a common denominator. I'm just looking for the answer. Okay, any questions? Okay. Let's do reading and interpreting a velocity graph. Okay. Anybody still need to look at 2? Okay. Let's look at a velocity graph here. Okay, so let's say I have a velocity graph here. And let's say I gave you the areas of these regions to be 3, 11, and 2. So this particle is moving left and right. Above is right, below is left. So what adjustment can we make with this area here? Yeah, we know displacement is going to be negative, right? This is going to be a awesome movement. Okay, so if I gave you area, I'm going to make that adjustment, positive and below. Positive is above, negative is below. Okay, so now I'm going to ask you for position here. So given x of 3 is equal to 5, that means at 3 seconds, this object is going to be on the x-axis, on x-intercept at 5. Find x of 10. So I want you to be able to utilize our final position formula. So here's the formula that we're going to be using here. And it's on your formula sheet. If I'm looking for a final position, I'm going to have to rely on my given position or my original position plus displacement. In other words, x of b is equal to x of a plus whatever that gap is between my 2 points. So this is however much progress I made movement-wise added to my starting point, and that's going to end up giving me my location. So we're just going to fill in this formula here. X of 10 is the unknown. X of a is my starting point. And what are my bounds going to be if I want to bridge the gap between my starting and ending point? What should my bounds be? Oh, here's my formula, right? What do you guys think? What are my bounds going to be?
10 over 3.
Yep. I'm starting at 3. I'm ending at 10. Okay. Make sure that your given location is always starting at the lower bound. So we know that we're starting at x-intercept of 5, and then we're just going to total the progress that we made between 3 and 10. So we go to our graph here. Between 3 and 10, negative 11 plus 2. So we're over at 5. We move to the left 11. We come back 2. We're going to end up at location negative 4 on the x-axis. Okay, questions here? Good. Okay, what if I gave something that was a little bit strange here? What if I said, given x sub 10 is equal to 8, find x sub 0. So now everything is backwards, right? I'm starting at 10, and I'm moving my way to my end. So, but same formula here. Final position, that's the unknown that we're trying to target. Given position, we have x of 10. But now, how do we write the bounds? What's our lower bound going to be?
10.
10, right? Because we're starting at 10, we're ending at 0. So we got to put a 10 here. Again, these numbers will always match initially, okay? Now, what's strange about this? Even though we're following the rules, what's strange about this?
You're decreasing in number
Yeah,
size.
we would prefer to read the graph from left to right, right? Reading from right to left, we got to do everything backwards. So is there something that we can adjust so that we don't have to think of everything backwards? Can I flip those bounds? And if I flip those bounds, what do I need to do to offset that change I'm making? Okay. Anytime I flip the bounds, I can flip the bounds, but what adjustment would I have to make?
Make it negative.
Yeah, change the sign. And now we can read the graph the way it's supposed to be read, and then we can make it. We have the negative out there, so we don't have to worry about having to trying to process everything backwards in our heads. So x of 10 is 8. And then we'll just total the values like we see it from 0 to 10, and then we'll just change the sign once we get around to it. So 0 to 10, 3 minus 11 plus 2. So this is negative 8 plus 2, negative 6. Okay. We're keeping track of the negative that we pulled out. 2 negatives become positive. So we end up at position 14. So actually, we start off at position 14. And then after everything is said and done, we're going to end up at 8. But we're able to work through using this formula. Okay. You guys want to do a U substitution problem or integral definite integral problem?
What was that we just did called?
I'm sorry?
What is that called that we just did?
Oh, this is interpreting velocity graph.
Sounds great. Thank you.
Explain the unit.
Okay, what do you mean?
I was just confused when you were talking about.
How the units are changing?
Yeah.
Okay.
Then the last one.
Right, right. Okay. So going back to the worksheet that we did in class today, are you comfortable with the process where position, velocity, acceleration are all changing units? So you're comfortable with position changing from meters to meters per second to meters per second squared. And you're comfortable with, if I'm going backwards, my integral is also going to change units. So integral of meters per second squared will turn into meters per second. Integral of that will become meters.
So an example going backwards. One of the problems.
Right. So let's say I told you the integral from 2 to the 4 of v of t dt. All right. So maybe from a visual perspective, So what's velocity? What's the unit of velocity going to be? Okay, let's say meters per second. Okay. But the area under the velocity graph, if you see that 3, what do you think that 3 represents? Okay. But this is going to tell us how far we traveled.
Okay. Yeah.
So if we traveled 3, what's the unit going to be? Still meter. It's going to be meters, right? Meters. So you see how the integral process changed my units? If I find the area, if I involve the area velocity times time, it's going to give me back to meters.
Okay.
So maybe this is helpful too. Velocity is meters per second, but time is in terms of, we're taking that rate, we're multiplying it by time. So this is also in terms of seconds. So when you have meters per second, and you multiply it with time, with another seconds, then these units are going to cancel out, and you're going to be back to meters.
Yeah.
So anytime you go through an integral process, you're multiplying by time. When you multiply by time, you're going to lose it. You're going to lose it from your denominator. So what's happening here is when we take the integral of ounces per minute is going to turn itself into ounces. But the reason why it comes back to ounces per minute is because we're dividing it by the time. So this is how many ounces there is divided by 9 minutes. So if you do out 25.8 ounces divided by 9 minutes, you're back to in terms of ounces per minute. So this 1 over b minus a kind of undoes, or unravels that integral process that we just did, or the units changes back to where it came from. Okay, let's see, use substitution problem. Okay, why don't we try this one? Depth integral from 2 to 6, 4x times the square root of x squared plus 19. Okay. What's the first thing that we do? Okay. Okay, good. I guess more specifically is we're going to do the in-depth integral first, right? The bounds is not the first thing that we look at. So we're going to just focus our attention on just without the bounds, but you're on the right track. Okay, so we basically are going to solve this problem without the bounds. The first thing we should always look for, can we expand this problem? So can we expand this problem? Can I do any of these steps for this problem? Can I distribute my way through this problem? What do you guys think? Or is something preventing me from doing that?
You can't?
Yes, that's right. We cannot do it because unless all these terms are resolved, I can't distribute through, right? I'm breaking order of operations if I do that. So if I have plus or minus inside the square root, we know that we're stuck, and we know we can't just rely on our power rule conditions. So good, we know we got to involve use substitution. So let's rewrite our problem using parentheses. And now it becomes easier to identify, right? What's our u value? And we know we're going to be targeting replacing dx as well. Okay. Good. So we're just going to go through our steps of u substitution. U equals x squared plus 19. Derivative is 2x. Solve for dx. Make our substitutions. And we'll see what goes away as we make our substitutions. Right? X squared plus 19 gets replaced with u. Dx gets replaced with du over 2x. And hopefully something will cancel out along the way. Okay, what do you guys see after I made those substitutions? Good. Good. So, but the important thing is that the x's goes away, right? It's nice that the coefficients clean up, but that's not as important. As long as we keep track of it, we're good. But yes, x's goes away. That's key. And if the x's goes away, we can reduce the 4 and 2 as well. We can pull the 2 out in front. And I can now rely on power rule. I can pull the 2 out in front. And now I got a perfect match with the power rule that I want to use. So what happens to the 1/2? All right, add 1 to the exponent. We get 3/2, right? Flip that fraction up. We get 4/3 u to the 3/2. And now that we found the antiderivative, now we can involve the bounds. Right, the bounds is now going to play a role. But am I going to be able to take the 2 and 6 and put it into this expression? Why not? Good. X is not the same thing as u. So this is where you have 2 methods to choose from. Either you do everything in terms of u, or you do all your process in terms of x. I'm going to do u first. Then convert the bounds. And the way you convert the bounds is there's our conversion rate. Okay, so put 2 in for x. And then plug 6 in for x. So there are my adjusted lower and upper bounds. Dump it into my expression. These don't clean up nicely. You can leave your answer unsimplified. No problems there. That's one method, okay? The second method is you take your antiderivative, you bring it in terms of x, right? You were going to do that anyways, so just get it in terms of x. And then you can use your original bounds without having to adjust anything. But you'll get the same answer either way. Either use 6 and 2 with your expression in terms of x, or you use 52, 55, and 23 for my bounds in terms of u.
So back to the beginning of the problem, I was confused on what you were saying before we found d of x. You were saying that you needed to check something else beforehand.
Right. I need to check to see if this is a problem that I can solve with just power rule. Because not every problem is u substitution.
So like if it was just x squared.
Right. If it was just x squared, then yes, we can just distribute that through. Or if it was 19 times x squared, we can still work with that. But anything like this, or anything where your parentheses has a binomial raised to the 10th power, where you don't want to be expanding, then you want to do U substitution. But let me show you an example of a problem where you don't want to use U substitution. But first, any questions about this one here? Okay, so here's an example. Is this something that we can solve just by expanding? This one we can.
Like you said, if it didn't have the, if it had like addition or subtraction.
You mean here?
Mm-hmm.
Well, this is safe, right? You don't see an ugly exponent here. You don't see an ugly radical here. So can I just do this? Can I just make this 4 minus x squared? Bring that x to the top? And then just distribute through without any issues? Two minus 1/2 is 3/2. Do you see how clean I was able to work from here to here without any obstruction? Meanwhile, what if I do this problem here? Now this is an issue, right? Because if I bring that x to the negative 1/2, there's going to be a 1/2 here. I can't distribute. Those aren't like terms. I have unresolved issues here. So this is a U substitution problem, but this one is not. Because if I move things around, I'm not going to run into any issues where I'm stuck.
Mr. Yang,
Yes.
can you go back to the end of the last question?
Mm-hmm.
Thank you. Got it.
Okay. All right, let's try another one of these. Okay. Does anybody have any questions, or were there any problems, any types of problems that you want to do? I'm just kind of picking and choosing problems for us.
So all the PVA type of questions.
Mm-hmm.
Maybe done all the calculators now.
Yeah, so you don't have to show your work, but I'm going to ask you for justification, I'll ask you for reasoning, I'll ask you for units, but you don't have to do any calculus by hand for those problems. All right, let's try this one here. Integral of 3x squared times square root of x plus 5. Okay, first things first. Can I just rely on power rule? Can I just rely on moving things around and getting it ready?
No.
Okay, what's my issue?
Parentheses.
Okay, more specifically, the parentheses itself is not preventing us.
X to the 1/2.
Yeah, the x to the 1/2, right? We can't distribute something through x to the 1/2 until this is resolved, and this is not going to be resolved because those aren't like terms. So we're kind of stuck, right? Order of operations, we can't move forward. So we know that we got to explore something beyond just expansion. So we got to pursue maybe use substitution. That's a possibility. So we got to rewrite the problem. Okay. What's our u value? All right. Are we going to be, is this going to work out cleanly? Is that x squared going to go away on its own? Because the power is not high enough, right? Once we get the derivative, it's not going to be a good match. But we're still on the right track. We just know that there's going to be something more we got to do. Okay. Okay. So du dx cross multiply. And we can make our substitutions. So unfortunately, we can't move forward because we don't have everything resolved. Now, let me talk about this, though. A lot of students want to do this. They want to say, well, I can do power rule here. 3x cubed over 3. U to the 1/2, that's u to the 3/2 over 3/2. I'll multiply those together, and there's the ending. Okay? That feels like an easier path, but it's not going to get us the right answer. When things are multiplied, they're kind of stuck. We can't split up, we can't pick and choose different rules when things are being multiplied. So this is our issue. The x has to find a way to be replaced. Do you see a way that we can get that x to be replaced with something equivalent? Is there a way to rewrite this so that everything we see in front of us is in terms of u?
You were plugging u minus 5.
Say it again.
U minus 5.
So this, right? We have something that's defining, connecting our u and x. So why don't we solve for x and substitute it into that expression? Good. So we're one step closer. But now we have a mess that we have to resolve, right? This is not ready for power rule, even though we are one step closer. Okay. Any questions from here to here? Good. Now we got to FOIL all this out, right? We got to clean all this up. We got to go back to our power rule conditions. But to do that, I'm going to rewrite it so that my binomial, I can square that. Just cleaner for me. If I have my single terms out in front, I can expand this out and distribute later. So careful though, we can't distribute this through yet. We got to FOIL this out. Okay, almost there. Add the exponents. Okay, now are we ready for power rule?
Yeah.
Everything is nice and clean, right? No issues, no denominator, no variable, no parentheses, no radicals. So now we can do power rule. Okay, replace every u value with x. So we got to make sure we go past this point, right? Got to keep reminding ourselves that u is a temporary variable. If you see u in your answer, that means we got to keep going. There's something else that we can replace it with. Yeah, double check my work. Oh, sorry, this is 5/2, right?
So does it matter at what point you're adding in C as long as it's in the final answer?
As soon as you find your antiderivative, a plus c should show up.
Okay.
So as soon as you apply power rule, as soon as you apply that process of adding 1, your integral notations goes away, and then plus c is going to show up.
It's a big deal if I'm just like working through it and then add C at the last step.
Sure, that's fine. Yeah, if you have plus c at the very, very end, you're good. Yeah. Okay, any questions? All right, feel free to send me a remind if you have any questions. But tomorrow morning, 7:15, I'll be doing another help session in the morning. Okay.
Thank you.
All right, take care.
Thank you, Mr. Young.
All right, take care. Let me know if you have any questions to remind.
Mr. Young,
Yes.
I had a question to remind you a little earlier, and I think
Okay,
it's
let me see.
It was just about the last test. I had saw
Okay, see you. You too.
that I had a few questions wrong, but it just said like -3 points. I was wondering if there's like a place where I can go to see like what exactly I got wrong, because I know that on some of the questions it like gave a description, but then on those 3 I was just kind of a little confused with what I got wrong.
Right. Okay. So let me see if I can find that. Okay. Let's see. Did you send me your test through email, or did you submit it through Teams?
I did it through Teams, but I know that it was just like 2 images. I sent like 2 JPEG files, I'm pretty sure.
Okay. Let me
Just take
see.
a picture of my phone and upload it through Teams.
Oh, okay. So you did send it to Teams. Assignment. Okay, number 4, 5, and 7, right? Okay.
Yeah.
So you see that third line on number 4, you foiled out the 2 plus 2 over ni, which is good. But then you see how there's still a minus in front of that parentheses?
Oh, okay, I see.
And so that minus has to end up distributing through to the 4, to the 8 over ni, and to the 4 over n squared I squared.
Okay.
So that's going to throw your answer off. So everything was kind of opposite signs.
Oh, okay, that makes sense. Thank you.
So that's the only thing. It's not going to show up on the test. We're not doing that definition on the test.
Okay.
So number 5. That looks pretty good. Let me see. Where did I? 82. Yeah, number 5 looks pretty good. I should have given you points back, so I'll give you those points back. Number 7.
Oh, okay. Thank you.
You brought the x to the negative 1/2 up. Yeah, I don't know why I took those points off. I should have given those points. So I'll add 6 points back.
Oh my gosh. Okay. Thank you.
So you'll get, so your steps look good. So I'll add those points now. I'll put it into Infinite Campus now.
Okay. Awesome. Thank you so
Yeah,
much.
but yeah, your work looks good. You moved everything correctly. So yeah, you should have earned those points.
Awesome.
Good.
Thank you so much.
Yeah.
I hope you have a great afternoon.
All right. Take care, Caitlin. Bye.
Bye, Mr. Yang.
Bye.